So this video is on characteristic polynomial with repeated roots. So consider an AR2 model with row 1 equals 0.6593 and row 2 equals 0.4856. Our objective is to fit the AR2 model, find row 3 and row 4, and find the variance of noise if gamma naught is 0.52. So we start with the Yule-Walker equations because we are trying to find the coefficients. So the model is xt minus phi1 xt minus 1 minus phi2 xt minus 2. So we'd like to find phi1 and phi2 first. So the Yule-Walker equations are row 1 equals phi1 plus row 1 phi2 and row 2 equals row 1 phi1 plus phi2. And we can write this in matrix form as row 1, row 2 equals phi1, excuse me, one row 1 and row 1 1 phi1 phi2. So we could call that matrix P, that as G, and that as phi. This would imply phi is equal to G inverse P. And you can find this using a scientific calculator. Such as TI-84. So you have to use the matrix functions in the calculator to find that. If we plug in the matrices G and P and find the inverse of the matrix and multiply it by P, we will find phi to be equal to, well, before I get that far, let me plug in the numbers here. So in our case, we would have 0.6593, 0.4856 equals 1, 0.6593, 0.6593, and 1. And now if we invert the matrix, we will get phi1, phi2 equals approximately 0.6 and negative 0.09. So now that we have the values of phi1 and phi2, the AR2 model is xt minus 0.6 xt minus 1 and plus 0.09 xt minus 2 equals 80. So that is our model. Now we have to find row 3 and row 4 in part B. So row 3 and row 4, obviously what we have is row 1 and row 2. We do not have row 3 and row 4. So how do we get to row 3 and row 4? We have to find a general expression for row k. So if you recall, we made use of the characteristic polynomial to find row k. So let's find the characteristic polynomial. So we could rewrite the model as xt minus 0.6 b times xt plus 0.09 b squared times xt equals 80. We have xt in common, so 1 minus 0.6b plus 0.09 b squared equals 80. So the characteristic polynomial is 1 minus 0.6b plus 0.09 b squared. That would be phi of b. And obviously that is a quadratic function, so we can use the quadratic formula. So the roots of the characteristic polynomial are call it r, so minus b, so minus of minus 0.6 plus or minus square root of b squared minus 4 times a times c divided by 2 times a. So that would equal to 0.6 plus or minus square root of 0.36 and minus 0.36 divided by 0.18. So this would simply reduce to 0.6 over 0.18, which is 3.33. So the roots are R1 equals 3.33 and R2 is equal to 3.33. So the roots are repeating. So there is only one root then. Let's call it R, which is 3.33, with a multiplicity m1 equals 2. The general expression or general solution for row k is row k equal to sum I equals 1 to v, sum j equals 0 to mi minus 1, and we have cij, k raised j, and r raised minus k. So row k would now equal to I equals 1. We have one root, so v is 1. The multiplicity of that one root is 2, so we'll just write it as mi minus 1 for now. Cij k raised j r raised minus k. If we plug in the value of I, we'd end up getting j equals 0, m1 minus 1, c1j, k raised j, and r raised minus k. m1 is the multiplicity of the root, and the multiplicity happens to be 2. So sum j equals 0, 2 minus 1, cij, k raised j, r raised minus k. We have I as 1 already, so we could rewrite it. 0 to 1, c1j, k raised j, and r raised minus k. So if we plug in the values of j, we have c10, k raised 0, r raised minus k, plus c11, k raised 1, and r raised minus k. So this would imply rho k is equal to c10, k raised 0 is 1, r raised negative k, plus c11, k times r raised negative k. There are multiple ways to solve this, but the best way would be to use matrices again. So we know the values of row 1 and row 2. It's given in the problem. Row 1 is 0.6593 and row 2 is 0.4856. So we are going to plug in k equals 1 in the general solution. So row 1 would equal c10 r raised negative 1 plus c11 times 1 r raised negative 1, which is c10 times 3.33 raised negative 1 plus c11 times 3.33 raised negative 1. So that would reduce to 3 over 10 plus C11 3 over 10. 3.33 is 10 divided by 3, and if we invert it, we get 3 over 10. So row 1 is equal to that value, that expression. So 0.6593 would be equal to C10 times 0.3 plus C11 times 0.3. Likewise, we can plug in k equals 2 in the general solution. Which would imply that row 2 would equal to C10 r raised negative 2 plus C11 times 2 r raised negative 2. So C10, the value of r is 3.33 raised negative 2 plus C11 times 2 times 3.33 raised negative 2. Which is C10 multiplied by 0.09 and C11 times 2 multiplied by 0.09. So C10 times 0.09 plus C11 0.18 would be equal to row 2. And we also know row 2, since row 2 is 0.4856, the equation now becomes 0.4856 equals 0.09 C10 plus 0.18 C11. So the two equations obtained using the general solution and the values of row 1 and row 2 are 0.6593 equals 0.3 times C10 plus 0.3 times C11. 0.4856 would equal 0.09 C10 plus 0.18 C11. So we could rewrite these two equations, which form a system of equations, using a matrix. So 0.6593, 0.4856 as a vector would equal 0.3, 0.3, 0.09 and 0.18 multiplied by C10 and C11. We'll call that matrix or that column vector U and that as V, and we'll call that as C. This would imply U is equal to V times C, which would give us C equals V inverse multiplied by U. So again, so we can use a TI-84 calculator and the matrix functionality in the calculator to find the value of C. If we invert V multiplied to U, we'd end up getting C10, C11 to be equal to 1.5 and not necessarily. End up getting -1 and 3.197. So this would mean C10 is -1 and C11 equals 3.197. So recall the general solution for row K is row K equals C10 times 0.3 raised negative K plus C11 times K times 0.3 raised negative K, which we can rewrite now as -1 times 0.3 raised negative K plus 3.197 times K times 0.3 raised negative K, which would imply that row K is equal to -1 plus 3.197 K multiplied by 0.3 raised negative K. So that is our general expression. Now that we have an expression for row K, we could plug in the value of K to find row 3 and row 4. So plug in k equals 3, then row 3 would equal negative 1 plus 3.197 k, well k is 3, so times 3, point 3 raised negative 3. Excuse me. And that value is 0.232. Likewise, we can plug in k equals 4, then row 4 would equal negative 1 plus 3.197 times 4 times 0.3 raised negative 4. And that happens to be 0.0955. So how do we find row 3 and row 4 for an AR2 model? Well, first we find the general expression. Once we find the general expression or the general solution, we can plug in the values of k equals 3 and 4 to find row 3 and row 4. As you can see, as the value of k increases, the correlation that we observe, or the autocorrelation that we observe, would decrease. So we started at 0.2320 for k equals 3, and it becomes 0.0955. So if you plug in k equals 5, 6, and so forth, those values would decrease as k increases. And lastly, part C wants us to find the noise variance. So the variance of the noise is related to the variance of the series, which is sigma squared x. Sigma squared x is simply equal to sigma squared A divided by 1 minus phi1 rho 1 minus phi2 rho 2, which would imply sigma squared x times 1 minus phi1 rho 1 minus phi2 rho 2 equals sigma squared A. Sigma squared x is given in the problem, which is 0.52 times 1 minus phi1 is 0.6 and times the autocorrelation at lag 1. So we have that to be 0.6593, and the autocorrelation at lag 2 is 0.4856. And we have phi1 to be 0.6 and phi2 as negative 0.09. So 0.6593 negative of negative 0.09 times 0.4856 would equal sigma squared A. So 0.52 times all of that. You plug all the numbers in, you'd end up getting sigma squared A, or an estimate of it, would simply be equal to .337. So in order to find autocorrelations at lags greater than k equals 2 in an AR2 model, we first have to find the characteristic polynomial, the roots of the characteristic polynomial. We use the roots of the characteristic polynomial to find the general expression in terms of k, which is right here. And then we have to find C10 and C11 using the known values of autocorrelation, which is rho 1 and rho 2. And once we have that, we can solve for C10 and C11. And once we have the values of C10 and C11, plug in those values in the general form to get that general expression, and we can plug in values, different values of k to find rho 3, rho 4, and so forth. The noise variance is related to the variance of the series using that formula. Now that we have phi1, rho 1, phi2, rho 2, we can simply find the variance of noise by plugging in the values that we know. An important note here: the root here is R 3.33 with multiplicity 2, and 3.33 lies outside the unit circle, and this would imply phi1 and phi2 are inside the unit circle, which we actually have. We have phi1 to be 0.6 and phi2 to be negative 0.09. They both lie inside the unit circle. This would imply that the series is causal and stationary. So, in short, if the series is causal and stationary, the roots of the characteristic polynomial would lie outside the unit circle, and the phis of the model would lie inside the unit circle.